Hey guys, as you know, integration by parts is one of the toughest ones to identify. It is not as obvious as, for example, when we have a partial fraction, which is when we have a rational function in front of us. And we usually try to use integration by parts after trying a substitution that didn't work. In those cases, that's when we start thinking whether we have a case of a integration by parts in front of us. In the realm of integration by parts, we have a few cases. So there are integrals that require integration by parts once. There are cases which we have to use it twice. There are even cases that we need to do a substitution and then integration by parts. And there's also the cyclic type. And what is a cyclic integration by parts? It's one then when applying integration by parts, you get back to an expression involving the original integral. And those are the types that we're going to do today. We're going to go through two examples. One which is very typical when we mix an exponential and a trig function with a product between them. The other one is less obvious. So let's get to these two exercises. All right, so on the first example, we have the integral from 0 to pi over 2 of e to the x plus 2 times sine of x dx. There's one thing that you can do in the beginning of this exercise, which makes it a little bit simpler. I'm not going to, but I'm going to show you what that is. You could rewrite this as e to the x times e squared and move this over here. So you would have e squared times the integral of e to the x sine of x. That would work just fine. But you can also carry this the way that it is. It's also important to remember the priority for choosing where your u is going to be. There's an acronym ILATE, I-L-A-T-E, that you can use and should use to choose what your u is going to be. So the top priority is for inverse trig functions such as arcsine, arctan. Then we have log functions such as natural log of x or log base 10 of x. Then we have algebraic ones such as x squared to x plus 1. Then we have the trig ones and the exponential ones. And whenever we mix, for example, a sine with a e to the x or some variation of that, meaning a trig with an exponential, we get a cyclic type of integration by parts. And in those cases, it doesn't really matter what you choose for u. You can choose u to be the trig one or the exponential one. Either way, it's going to work. So let's say that in this case, we're selecting u to be e to the x plus 2, meaning that du is e to the x plus 2 dx. Our dv is sine of x dx. Therefore, v is the integral of sine, which is negative cosine of x. Now, what are these u's, the u's, v, and dv's? These are the terms which go into the formula for integration by parts. So we have the integral of u dv, which is equal to u times v, minus the integral of v du. And the definite integral version of this is from a to b. We also evaluate this term from a to b, and this integral goes from a to b as well. So we have u e to the x plus 2 times v negative cosine of x minus the integral of v, which is negative cosine of x. So I'm going to flip this sign right here, times du, which is e to the x plus 2 dx. All of this ranging from 0 to pi over 2. Now notice that you didn't get the original integral on the right hand side, but you will after the next iteration. We need to use integration by parts once more. Instead of selecting functions to be lowercase u and lowercase v, we're going to select them to be uppercase u and uppercase v. So we keep the consistency of the letters, but we're actually also changing them because we couldn't call different things the same name. We couldn't attribute the same variable to different things. So using capital U and capital V is a nice workaround. So we have capital U as e to the x plus 2, meaning that d capital U is e to the x plus 2 dx. And then we have d capital V as cosine of x dx, which is this guy right here. And v is the integral of cosine, which is sine of x. So for this integral specifically, we have capital U, capital V from 0 to pi over 2 minus the integral of v du sine of x e to the x plus 2 dx. To make it look even more similar, because it's the same thing as this one, I'm just going to change this order functions around. So we have e to the x plus 2 times sine of x dx. Now notice that we always had on the left hand side the integral from 0 to pi over 2 of e to the x plus 2 sine of x dx, and that's exactly what shows up on the right hand side as well. So let me copy the left hand side again, and given that this integral is exactly the same as this one, we have not 1 but 2 times the integral from 0 to pi over 2 of e to the x plus 2 sine of x dx. We still have left on the right hand side this and this, which are both evaluated from 0 to pi over 2, so we can just place everything inside a set of parentheses and evaluate it from 0 to pi over 2. Substituting the upper bound, we have negative e to the pi over 2 plus 2 times cosine of pi over 2, which is 0, plus e to the pi over 2 plus 2 times sine of pi over 2, which is 1. All of this minus negative e to the 0 plus 2, negative e squared times cosine of 0, which is 1, plus e to the 0 plus 2, e squared, times sine of 0, which is 0. So these guys disappear, and we have e to the pi over 2 plus 2 plus e squared. Now that is equal to 2 times the integral from 0 to pi over 2 of this. Therefore, the final answer is half of that, which you can leave like this, or you can factor out a e squared as well. So you have e to the pi over 2 plus 1 times e squared over 2. All right, so now that we're done with exercise 1, let's jump to exercise 2, which is much less obvious. In this case, we don't even have a mix between a trig function, a sine or cosine, for example, and an exponential one. In this case, we have the integral of sine of ln of x dx. Now, it's already hard to spot what u and dv should be because we have a composite function in this case. Now, you may observe, however, that we don't even have a choice. U has to be sine of ln of x, and dv in this case will be dx. And this means that du, which is the derivative of sine of ln of x, will require the chain rule to be found. So we differentiate the outside function first. So we have cosine of whatever's inside, in this case ln of x, and then we multiply by the derivative of the inside function, 1 over x, and then we have dx. And given that dv is dx, that means that v is equal to x. So we have the following: u times v minus the integral of v times du. So x times cos of ln of x times 1 over x dx. Now we can definitely simplify these x's and 1 over x, which gives us the integral of cosine of ln of x dx. Now you probably see where this is going. We need to use integration by parts again, and in this time we're going to use capital U and capital V again. We keep the formula for integration by parts consistent. The integral of u dv is uv minus the integral of v du. This time we have capital U as cosine of ln of x, which means that du is going to be the derivative of cos negative sine, and we place the ln inside and then multiply by the derivative of the natural log dx, and our dv will be again dx, which means that v is equal to x. All of this corresponds to this integral right here. So we have x sine of ln of x minus uv minus the integral of v, which is x, du, which is negative. I'm going to change the sign right here. Sine of ln of x times 1 over x dx. And there is it, the same integral that we have on the left hand side over here. Just be careful when you distribute this negative sign over here. So we have minus x cosine of ln of x minus the integral of sine of ln of x dx. Now these two are identical, meaning that they can be rewritten moving this one to the left hand side as 2 times the integral of sine of ln of x dx. So we have x sine of ln of x minus x cos of ln of x, and then we divide everything by 2. And the final answer is 1 over 2 times x sine of ln of x minus x cos of ln of x. Don't forget the constant in this case, so plus c. And there we go, 2 examples of cyclic integration by parts.